S is defined to be, this is,
Oh, I need a new page.
defined, can't spell defined, defined as, so this symbol, colon with equal to sign afterwards, means defined as, and the set is 1 over n such that, and they use dashes, but we don't like dashes, so we're going to use this, such that n belongs to set of natural numbers. The infimum,
Is that the GLB?
GLB, infimum of S equals 0. All right. So the best way to understand this is by actually, we can do both the number line and the set. Let me do the set first and then the number line. So it will be to the left where there is no lower bound.
Yep.
And so towards the left it goes on forever, kind of.
Well, it completely approaches 0. So
Yes.
That.
Yeah.
It's an open
Hmm?
It's an open bound. Okay, the GLB is open.
Oh, so the GLB is sitting out here.
Yep.
And then here, any number will be an upper bound. So we could have 47.
There's no upper bound.
There is.
No, we've proven that there isn't. Oh, this is for the, there could be for the set S.
Yes, there is an upper bound for set S.
Only if we decide that there is.
And this is the largest element. Therefore, this is the LUB.
Oh.
So the key thing for LUB is that if it's going to be in the set, it better be the largest element of the set, which it is, 1. And therefore, this is the LUB. 47, 2 million, 1 zillion, all of those are upper bounds for this set. Down here, as you were saying, it approaches 0 but never gets there. So the 0 is not in the set. So 0, 0. So this is largest element. LUB is in the set. This is just a quick review, right?
Yep.
And here, there is no smallest fraction of the form 1m. You'll always get a smaller one. Always find a smaller one to the left.
Okay, so this is tying together what we just did. Here we just did, and then one of the earlier things that we did, where we said we can always make.
And when it comes in, it will know, because it will tell us.
Yep.
When it's using the two things we just did. And then this is GLB. This is infimum. And it is not in the set. And also, just a note, the set has no smallest fraction. All right, so that's our picture one. So I'm going to delete all this and keep the set. And keep this information here, GLB or infimum. And this is irrelevant to our situation, but we have it there just for our information. Now, let's do the number line. Do we really need the number line now? Not really.
So this kind of like this.
This is good enough, right? If we were to, we would just have a number line going like this. And then, well, I'll just delete it. And what you have is half, 1/4, 1/3, 1/5, 1/9, and it gets more and more dense here.
Oh, so now we've got.
Yeah, because everything has to be 1 over, right? And so this will go into 1 over billions and zillions all the way, but never getting here.
So density at 0 or right before.
So 0 is
incredibly high.
yes, and very sparse here. So the 0 is not in the set. Actually, if I do the reverse, so the 0 is not in the set, and everything in the red is in the set, and it slowly becomes sparser. And after 1, this is included in the set.
It's like a little microcosm of infinity.
Yeah, right there. All this is mind-bending shit. Like, wow, this can go on forever. There was these Hindu mathematicians in India who were doing all this way back in the day. Yeah, they were proving theorems and shit. Okay, randomly. Priests, because they had time. Okay, so in fact, this does kind of, you can see that too here, right? Sparse.
Yep.
And then
Builds up.
yeah, okay. So we could write that here, infinitely many one ends, and then fewer and fewer until there's just one. Okay, is that the proof? All right, so proof. So what are we trying to prove? We're trying to prove that this set S defined like this, its greatest lower bound or infimum is 0.
Yep.
And in other words, I think in this case, we work with this because this is already the result. You can't do much with that, right?
Mhm.
So we have to work with this and see how we can take this information and get there. So let's see what the book does. So the book goes, since S is not equal to the empty set, or S is non-empty, and this, since S, that non-empty set S is bounded below by 0, so I wrote in my notes, this thing, the people who are writing the proof can say this because they worked out the set like the way we have. They actually wrote it out to see what it looks like and where the values that are going towards the lower bound are getting to. So they actually drew it out just like we did. So this whole thing is, so this thing is from this business. Because so what is this business? This is understanding and visualizing the definition, the definition given of set S. And that allows us to write the first line confident. I think I don't see. So it's kind of off, but hey, okay. I don't like this, but that's how it is. So it has, now it says, because it is bounded below, just like when it's bounded above, it will, and if it's not empty, it has an LUB. If it is bounded below with 0, and it is non-empty, it will have a GLB.
Okay,
Yep.
so it's kind of reverse.
Reverse, yeah. So it has, since this is true and this is true, the two conditions for the completeness theorem
They
property,
hold.
they hold. It has an infimum and infimum is basically greatest lower bound. And right now, all we know is that this is an upper bound, right? A lower bound, right? This is now, this has been identified as a lower bound. So it has a lower bound, it is non-empty, therefore it has an infimum, and let's give it a name. And it says, and we let W be defined as so what we have to do is we have to show this W is equal to 0. Yeah, we have to show W, because from this, the only information we have is that we were able to figure out by drawing it out and reasoning with the way the elements are that there is a lower bound 0. And it is non-empty. So that gives us this variable. That tells us that there is an infimum. There is a GLB of S. Let's call it W. It could be 0. It could be something else. So let's find out. And that's when that there is no smallest positive real number comes in. Yep. It's coming. To some of us, it is clear because I read this in the textbook. It is clear that W so what is W? Is W? Is it going to be a negative number or to the right of the? So this picture right now, all we know is that it's right. All we know is this is a lower bound, right?
Well, so what we know is W could be less than or greater than or equal to.
It needs to sit here, right?
Yep.
And can it be in the set itself? No. because the set doesn't have a number inside. There is no smallest number
Yep.
that is smaller than the rest of them. As soon as you locate a smaller number, you'll find another one to the left of it. So it has to be outside,
Yep.
not in the set. So W will be outside, not in the set, and maybe it will sit right here. So let's stick it here. So this is our upper bound, and our W sits here. So this is our potential. So this is our candidate, GLB, greatest lower bound, and this is our lower bound. Okay, so it is clear that W is therefore greater than or equal to 0.
That is clear, because we're dealing with the set of,
Yeah.
set S isn't on the natural number line.
And in fact, if you, yeah. And in fact, if you look at it here, there is no, between 0 and this, W cannot sit. It really cannot, right? Because there will be another W that's smaller.
Yeah.
And another W
We
that's
can divide W by
yeah,
2.
yeah,
and divide it by
yeah.
2.
So the candidate GLB is not going to work. This is our candidate. This is the actual one, as the theorem says. Okay, so this is like, actually they're going like direct, finally.
Yeah, finally direct.
So you do some, all right. And in fact, yeah, that's good. For any, now of course we're going to bring in the epsilon, because we want to push this guy. We want to see how far the W moves around.
See if we can break W.
Break it, squeeze it. All right,
That's it.
for any epsilon greater than 0, and that's the rub. This word any gets everybody into trouble. And Archimedean property, all Archimedean property is saying is that this is Archimedean property.
Yep.
Thank you. I'm like, well, that doesn't work. Okay, so what that is saying is that you give me an X, give me a real number, and I'll find you to the right of that real number will be a natural number. Okay, now, what is this? This thing here is this. For any epsilon, if you have a real number X or a real positive number epsilon, then there will exist to the right of the epsilon a natural number. So they're applying this property by, they get to apply this property by just writing this. They write this and they go, look, this is a positive real number. And Archimedean property says that any positive real number to the right of it, there will be an n. So they can bring in this n here. Okay. And so they go, implies that there exists an n that belongs to the set of natural numbers, and then we go such that And this is where they go a little wonky. They go 1 over epsilon is less than that n. So that's what they pulled. Okay, so what they're doing is this epsilon and this epsilon are still positive numbers.
Yep.
This epsilon is another epsilon. Okay, so it's kind of like this. Remember we did E equals half of A?
Yep.
And here what they've done is, and this was epsilon 0. This is our new epsilon. And it says for any, this is, you can say our new epsilon zero, sub 0 is 1 over epsilon. So this in fact is another epsilon. And it is less than n, which they just, so we have an epsilon, and the Archimedean property says, therefore, n will be to the right of this epsilon. And in fact, it will be, there will exist an n, which will be right of 1 over epsilon as well. Because this is just another very small epsilon. This is our new, because we could, yeah. Okay, and then what that does is,
Smaller than?
yes, it has to be.
Okay.
So because this is the Archimedean property. Give me a real number, and to the right, I'll get you a natural number.
Oh, yeah, okay, so 1 over epsilon is our real number, that's our x.
So let me write that here. Real number. And then a natural number
To the right.
to the right.
And it's only less than, it's not equal to?
And that's a very good point. And they only do less than, I don't know why. And let me double check with our Archimedean is less than and equal to. And I think the reason is quite simple. I just saw it. You know why? Yes, sir. No, I'm not going to tell you. No, okay. 2.4. The reason is this, sir, is a fraction.
Oh.
So it can never be equal
Yeah.
to a natural number 1, 2, 3, 4.
What's epsilon equal?
Which implies,
Greater than that.
or something, which implies, and they're pulling all the tricks that make math hard, which is what you were just saying. We multiply, what do we do? Yeah, we divide both sides by n. So we have and we why am I getting confused?
Well, if we're multiplying both sides by, or dividing both sides by n?
We are, no, we're just moving cross multiplication. This goes here and this goes here. Yeah, why does it look weird? But anyway, what happens next is this. 1 over n is less than epsilon. Okay, what does that do? That is telling us that what is this form?
That forms our set.
That's the form of each element of our set. So each element of our set is less than this positive number epsilon. Okay, once we have that, because now comes the 219, because 219 needs 0, A, and
Epsilon.
epsilon. we got this part.
Oh, because now we can move. Wait, so then 1/n has to equal 0 for epsilon to be greater. And
We're gonna have a little, something a little longer, and then we'll bring it downer, and then we'll be done. Okay, so next step is, therefore we basically have that, therefore we have epsilon and this guy is less than, it's greater than any element of set S better be bigger than GLB.
Oh,
Infimum.
Yep.
Or equal to, right? That's the definition of that. So we get W here. And then we've already stated that W is greater than or equal to 0. We have this classic situation. And since, do it here, but since epsilon greater than 0 is arbitrary, it follows from, now that theorem comes in, that there is no smallest real number. Theorem 2.19, no smallest positive real number that W equals 0. Okay, so they didn't pursue this, but I am going to, so there are too many terms for my liking. So let's reduce it. And the theory here is, what does this imply? Oh yeah, okay, so how do we, and we're done. Theorem ends right here. This is the Helmholtz. Because this is what we set out to prove, that W is the infimum of S is 0, right there. Okay, so, and this is called the Helmholtz, H-E-L-O-M-O-S, Helmholtz. Okay, W is less than or equal to this and smaller than epsilon, right?
Yep.
Therefore, W is less than epsilon.
Yep.
So we can write this as W is less than epsilon. And then we can bring this guy here. And this looks like our 219, exactly. And this implies